Oh, hell yeah. Now, this is number 3. This is a challenging problem. You know what I mean? They call it a class 3, whatever that means. Anyway, but it's physics book. We're doing this. You know what I mean? Everyone's physics book from college. And what we got going, I love these. Well, I hate them. This is like my least favorite because they're at some point we want to get to this diagram where hell yeah, and then the pack's in the air, hell yeah. Okay, do no more, and maybe do that, you know what I mean? But the first setup is like, well, what's the initial, and then they're saying this is x, you know what I mean? Cool. So at some point x is 0. Okay, so let's do that. Let's do that initial condition, you know what I mean? Well, we'll even do it now. I don't know why I did that, but anyway, so there you go. So and then we'll just do it, whoop, 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 de-scoop, de. So anyway, so x is 0. So here's the boy on there. There you go. And then here's the pack right there. And you can draw circles or whatever. But there's the pack, and there's the boy. You know what I mean? Half of it, this is just chapter 2 physics stuff. And you know, anyway, you're trying to do physics and so it's okay that these are just points, you know what I mean? Kind of one-dimensional, two-dimensional physics. Okay, well, now this problem takes like 20 minutes, but we'll just go right to it. So anyway, and in the second one, they actually give you, like, hey, this is 6 meters, you know, whatever that is, 18 feet or something, 20 feet. And then the boy's velocity is 2 meters per second. Okay, so that's interesting. So let's say you were just pulling the rope 2 meters a second, you know what I mean? Well, how long is it going to take to go 6 meters? It's going to take 3 seconds. Okay, but if the boy's walking this way, you know what I mean? How long is it going to... It looks like it's probably going to take a little bit longer. And the reason is like if you're just right here and you're just... this looks like it's walking downhill, but it's not. If you're just walking from here to here, the rope doesn't increase in length very much. You know what I mean? We'll just draw something in. You know, compared to this initial condition of there's hardly any difference between this line and this line. This line just lengthened a little bit. Oh, okay. So I think we got it. And so even if it's at a 45-degree angle, you know what I mean? Maybe that just means this is 6 meters down here. And then this distance right here would just be 6 squared plus 6 squared square root of that, which would be 36, you know, it'd be 72. Square root of 72. Square root of 64 is 8. You know, let's just say it's 8, friggin' 8. So this would be 8. And, oh, so that gives us our first initial condition. What the hell is the length of this rope? Well, if this is 6 and this is 6, like for you know, let's say this length is 12 meters. Okay, perfect. And then you got 8 meters here because you just did this Pythagorean's theorem. Well, you know, continuity. If this whole thing is 12 and you just pulled out 8 from the top of the tree, well, guess what? This is 4. So then that means the pack's 2 meters off the ground. So even at a 45-degree angle, this pack didn't move hardly at all. But then when you go like from 40 to 60 degrees, you know what I mean? You bought some fancy mustard because this pack is probably going to reach the top or something. Anyway, and I didn't even do that. But so what they want to know, shall we read it? To protect his food from the hunger of bears, a Boy Scout raises his food pack. Got it. He walks from a vertical rope this way 2 meters. Anyway, show the speed of this pack is this friggin' equation. Now, this equation is a function of this x term, you know what I mean? And then so we actually have to get, so that's where your mind explodes. It really does. So the first thing you need to do is to get a relationship between this x value right here and this value right here. Because if you get a relationship between this, you input this and you export, or whatever they say these days, this value right here, you will know the height of the pack. So let's say in 1 second, at 0 seconds, the pack's on the ground, you're on the ground. But in 1 second, you might be over here, and then the pack is up here. So now you actually know the velocity of the pack, or the average velocity. And chapter 2 stuff is like, hell yeah. So you have, average, velocity average, change in x, change in time. So even though we're saying this is the x direction, okay, let's just do it right now. This is height. We're going to call this the height direction, h. You know, it could be x, y. But anyway, we'll do h. Change in h, change in t. That's going to be your velocity. So if we know h at final minus h at initial, at change in time final minus time initial, this could also be h2 minus h1, t2 minus t1. So we know the initial condition, h is down here, nothing happening. At 1 second later, x is over here, but guess what? H is up here. So we know the average velocity h average. Cool, cool. Let's throw some more time on the clock. All right, hell yeah. Now let's get to it. Because even for me, you know, that's why I'm kind of taking my time. I don't want to do the numbers approach. The easiest thing to do is take it. Yeah, the next problem says, hell yeah, throw in 6 meters right here. This is 6 meters. And then it just makes it a little more simple. But so what I'm going to do is I'm going to call this h. So this is h, whether it's 6 meters or not. But this whole thing is h. Cool. And I'm going to call this the hypotenuse, h. Now, I just think it makes sense for me because this is going to be h over here. Now, this is a function of x, you know what I mean? And, yeah, so these h's are not the same. Okay, so let's not confuse it. But this is our first equation, that the length of the rope, we said the length is 12. So we're just going to say the length of the rope is h plus h. And I'm gonna reserve the other thing, the other equation that makes it just make more sense for when we get there. But just hold this thought, because you could make this equation a little more simpler. You know what I mean? But anyway, so now let's go over here. So now you have you know that you can take like this squared times this squared is equal to h squared. That's the Pythagorean's theorem. But now we know this whole thing is h. Cool. But how about just what's this? And then what's this? So that's where, with these problems, especially if you have like, hey, this is h, but then you have a part of it. Sometimes they would do like, hey, this is just change in h. Well, I don't even like that either, because your velocity will change the h. You know what I mean? So we're just trying to be like, what's it right now? So I'm just going to call this ht, because it's at the top. So this is the top part. This is hb, the bottom part. And I think that makes it now real simple. And now we have another continuity equation. H is equal to ht plus hb. And even just right away, you could also say that then hb is equal to h minus ht. And maybe your brain don't work that fast and you're not ready for that. But yeah, so even with these, we're just trying to find some sort of continuity. So now let's write our Pythagorean's theorem. You're saying that Pythagorean's theorem says x squared plus h squared is equal to this big H squared. Cool, cool. And look, we even have like h over here. We got h right here. Okay. And maybe this is confusing too. But this h is definitely not that h. So we'll come back to this one. Maybe this drawing was, wrong or something. But it's still a function of x. You know what I mean? The length don't change. The length really isn't a function of x. This h is also not a function of x. This height from the top of the tree won't change. So this is a constant, but this is definitely h of x. It's changing. All right, so now let's just throw things in. You said that this was h. Is it? I mean, do I even want to do this? Well, let's try it. Let's try. So we got. Oh, and then just a second. Oh, no, we're saying this x is actually equal to this full h. I'm glad I caught myself. You know what I mean? And so we just want to know what this h is. So h is equal to the square root of x squared plus h squared. Yeah, so I was even going to throw this in right there and probably just confuse the hell out of myself. But now we have this. And now you're just like, well, shoot. Now I don't know maybe what's happening. This is where I have h. And where else do I have h? Hell yeah, I got h up here. So we're going to use this equation now, that the length of the rope is equal to h plus this h, which is square root of x squared plus h squared. Let's throw some more time on the clock. All right, hell yeah. And then we also know that this length, oh, see, this is the thing. You know, this kind of helped me out. There's like, okay, the rope's got a full length, you know what I mean? And this length can't change. And it's h plus this h at its initial condition. Oh, whoa. But over here, you know, no. So over here, the length of the rope is actually equal to h plus ht. You know what I mean? So actually, maybe this is the equation that you'd want to use. But the other way to simplify this up is to say, hey, because this is a function of x, but this don't change. This h don't change. You can say the length is just 2h. It's just from the bottom of the tree to the top, back to the bottom. So if we put in length as 2h, even this one will work out really good, because now we got 2h is equal to h plus square root of x squared plus h squared. Okay, and now we can go 0 is equal to square root of x squared plus h squared, and then we're gonna minus h. Okay, cool. And but at some point we actually need to find out what the hell HB is, and I think that's where we're definitely going to use this equation. Is that the length of the rope is equal to h plus ht. Holy hell! Now I'm totally confused. Okay, so this is such a bummer. Yeah, for any value of x, this h is going to be the square root of x squared plus h squared. This is a constant. This will change. So this is the value of h. Okay, got it. And if we throw that value in here, we're going to get length of the rope is equal to h plus ht. So now we're introducing ht, and I think that's important because we can go from ht to hb. Because if we introduce ht, that's also just saying ht is equal to h minus hb. And I'm glad I got confused on this one, because you actually might find easier ways to get there. But it's just like, yeah, I just want to throw all the continuity equations that I can at it, knowing the length. Anyway, so let's do it. So let's just do this. Length is equal to h plus ht. And then we got, so we can throw this in for h, and we got the square root x squared plus h squared plus ht. But now we can throw in the L is equal to 2h over here. So we got 2h is equal to, and then we can throw for ht, we can throw, that's just h minus hb. So there you go. Finally got it. Holy hell. And that took me a little while. And this video is not clean, you know what I mean? It's not my best work, but it wasn't the best explanation on why this made sense. It seemed like there was too many continuity equations, but definitely starting over here and then saying that this length is always going to be whatever h is plus ht. It just happens that at the initial condition, ht is equal to h. You know what I mean? Because right here, hb is equal to 0. I think that makes more sense now. Because right here, this height hb is 0. This height ht is just equal to h. But because the tree is only at height h, that h, this distance never changes. So when we do our square root, you can always just do x squared plus the constant at h squared is going to equal this hypotenuse. Hypotenuse plus this little length equals our original length. Our original length was just 2 times h, you know what I mean, this constant. So there you go. 2 times h is the constant. This is h, you know, the hypotenuse, plus ht, which ht is just the full h, extra stuff, you know, the full constant, minus hb. Cool. Now we can just get hb. We're just trying to isolate hb. So let's take hb to the other side, and now we can fully equate that hb is equal to x squared plus h squared. And I don't want to do this wrong, but it's minus h. Now, will that make sense in the end? Hopefully. Yep, okay, there you go. There's HB. Finally got it. I need a new sheet of paper, and I don't want, so I'm just going to get a new sheet of paper, and I don't want to use this one because we'll use this one for with the numbers and maybe do it one more time. But we'll come up here. Finally, HB is going to be, so if we throw in any value of x, even a small one, let's say we throw in 0, well, then we're just going to have h squared here, and then the square root of h squared is just h, and then we're going to minus h. Well, guess what? That's going to be h minus h. Height of b is 0. Perfect. So this equation checks, and even when h is at the top, we're going to have, I don't know if we should, no, we can't do that one. Can't do that one. So yeah, for any value of x, you'll throw it in here. Now, if this thing is ever greater than the h, then you can't go higher. You know, this thing is a function that will continue to infinity, but because you have this tree here, you know what I mean. Once this value becomes 6 meters or greater than 6 meters, your equation don't make sense no more. Even though this equation, you know, will have you know, it'll just be out here anyway. All right, more time on the clock, and maybe I'll switch a little battery and take a little break because now we got to figure out what the velocity of this bag is. So we have to go change in hb divided by change in t. And when we do that, this is similar to change in hb. No, I'm sorry. This is similar to d, like your instantaneous change of b times your instantaneous change of t. So I always like to use this caret, you know, change in height, change in time, because it gives you the average. This will give you the average velocity over a window. But when you make this smaller, now you can just throw hb into the equation and take the derivative with respect to t. But guess what? Do you see t in the equation? I don't see t at all. I see x. So this is what you do. You use the chain rule. So the chain rule says that the change in dh dt, we'll just call it dh dt, is equal to well, it's going to be the change in your height, you know, with respect to x. But are these equal? No, these aren't equal, because this is respect to time, this is respect to x. So now you got to multiply dx up here and then divide it by dt. Cool. So now you can take the derivative with respect to x, what we have, but this won't equal because your change in height of b divided by change in time, this is literally the definition of velocity of hb, the velocity of the backpack. But what we can do is take the derivative with respect to x. Well, cool. If you do the derivative with respect to x, you still got to multiply by dx over dt, because when these cancel, then you just have dh of b over dt. So now you have the velocity of the bag. So anyway, so we can take this derivative and multiply it by this. Now what's dx of dt? Well, guess what? That's the velocity of the boy. So cool. So this is a total constant. They give it to you in the book, and we just call it velocity B, velocity of boy. All right. I'm going to charge up my battery, charge up the light, and I'll catch you on the flip side. All right. Hell yeah. Now welcome back. So we're going to do the chain rule, and this is going to be just real simple. We just take the derivative of you know, the height of the backpack divided by dx. And then we'll just take this on its own, And then once we find out what this is, then at the end, we'll hopefully not forget that we got to multiply it by this constant. And it's just nice to know that this is a constant. Okay. But if it wasn't, if this wasn't a constant, well, no, let's not even get into that. They gave it to us. So let's do it. Because we got to do it again to get the acceleration. Because that's also what they want to know, the acceleration of the backpack. Holy hell. So we got to differentiate once. And then acceleration is also change in the velocity of h of b divided by change in time. So that's what we're going to find. We're going to try to find the velocity of h and b. Cool. Once we get that, guess what? We're going to have to differentiate by the change in time. And there still won't be a t. There still will not be a t in this equation. So we got to do the chain rule again, which is saying dvh of b divided by the change in x. You know, we can change x and then understand something about the velocity. Is going to be dx dt. Hey, that's the same thing right there. So that's, again, velocity of the boy. So this acceleration is a function based on velocity of the boy squared. You know what I mean? And then we'll do that one too. And this is, because I was just like, I kind of answered my own question. It's just like, I never really liked the chain rule because it just seems hocus pocus. You know what I mean? But it's not. Because that's why I like numerical methods. You throw this crap into, even if you throw this into, because we have an equation. If you throw in x, let's say you throw in x, you know what I mean, at time 0, and then x at time 1/10 of a second, 0.1 seconds. You know what I mean? And you could do that. You just throw in, you know what I mean? You know, if it's 2 meters per second, well, if it's 1 meter per second, 1/10 of a second, you're going to go 0.1 meters. 2 meters, you're going to go 0.2 meters. So there you go. At t is equal to 0.1 second, your x is going to be 0.2 meters. So you could throw in 0.2 here. Let's do it. 0.2 squared plus 6. 6 squared. Square root of that. Minus 6. Okay, so this height of the backpack, like I said, because it's a pendulum, and if you want to see that one more time, you know, you tried to go a little bit, you can go quite a bit in this x direction right at the beginning. And the length of this rope hardly, I mean, because you're talking a circle here of a radius. So this change in height b is just infinitesimally small. And I'm glad I did that, because even just right here, at t equals 1/10 of a second, change in height of the backpack is 0.003 meters, where x is 0.2 meters. That's substantial. 2 meters is 0.2 times 100. That's 20 centimeters. You know what I mean? That's a 3/4 of a foot. It's cool. That's 8 inches. Cool. And anyway, hope you got all those metric conversions. A little side note on metric. Yeah, 100 millimeters. You should definitely know that's 4 inches. You know what I mean? So that means that, you know, 0.1 meters is 4 inches. And I didn't, you know, I first took, anyway, so do whatever you need to do to know that that's 8 inches. Cool. All right, so we're going to differentiate this. But what I was talking about Excel, because even, I got an idea for how I can kind of teach myself the chain rule giving, because that's what I wanted to do. Yeah, back to here, I just got a little sidetracked. So we can find the change. So we're going to use this. This is our average. I love this equation because it says, hey, if we just take the change in height of the backpack and over some sort of time period, and if this time period is real small, 1/10 of a second, and then the change of the height of the backpack was even really small, 0.003. So that's 0.003 divided by 0.1. Hell yeah, the velocity of the backpack is 0.03. Okay, and this also brings up one of the questions. They're just like, okay, let's say this boy just goes out to infinity, because this rope, it's not a backpack, it's just a pile of rope, infinite amount of rope. So you have an infinite amount of rope you can pull, and by the time this Boy Scout's just out to infinity, this is going to be a 90-degree angle, and the velocity of the boy is still going to be 2 meters per second. But it's just going to be, so the velocity of the rope right here is going to be 2 meters per second. So that's the limit. So when you start out, the velocity of the rope's like 0. You pull a little bit, like we showed, you hardly get any velocity of the rope. But once you get substantially out here, and you don't have to be out to infinity, this velocity of the rope will approach the velocity of the buoy. So that's kind of the cool thing about some of these equations is, you know what I mean, that they approach a certain number and then kind of stop at that number or never reach it. All right, let's throw some more time on the clock. All right, hell yeah. So how can we throw that into Excel? Well, you first take time is equal to 0, and then you go 0.1, 0.2, 0.3. And then in Excel, you take x. And we already know that x is going to be 0.2, 0.4, 0.6 if our velocity is 2 meters per second. Okay, because once we get up to 1 second, our velocity will be 2. So this is just double. Cool, cool, cool. Now you can take now I don't like to do change. Everyone likes to do like, hey, let's call this the change in height of the backpack. Oh, hell no. No, because change in height of the backpack, it's too much associated with the velocity. So I just like to do, you know, at a certain time, the height of the backpack is going to be based on this equation. And we already said the height of the backpack right here is going to be 0.003. And, you know, even if we put this one in, it's going to be, let's do it, 0.3, no, 0.6. If our x is 0.6 meters, hey, that's substantial, squared, plus 6 squared, square root of that, minus 6. All right, we're kind of picking up speed, but not much, 0.03. So now our h is 0.03 meters. So if we said, hey, this is our time interval, change in time is 0.3 seconds, and our change in h of b, see, this is change in h. It's starting from initial position and going to there. This is going to be 0.03. Cool. So now our velocity average of the height of the backpack, or the velocity average of the backpack, yeah, I guess we're calling it height of backpack velocity, is going to be change in the height of the backpack minus change in t. And then initial condition, so it's final minus initial, and so that's going to be 0.03 minus 0 divided by 0.3 minus 0. So now we got 0.03 divided by 0.3. Hell yeah. Velocity is 0.1 meters per second. All right, so the backpack is increasing in height by every second. Hell yeah, it's increasing in height by 10 centimeters, 2.5 inches. Okay, cool. No, that's not even right. 0.1 meters. That's 100 cent. Yeah, no, that's 10 centimeters. Holy Toledo. 0.1 times 1,000 is 100 millimeters. Yes, 4 inches. Yeah, anyway. Height of the backpack increases 4 inches. Cool. All right, so, and I kind of screwed myself over here. But now once we get all these values, we can find, you could just take the change in height of B, and then you could say, what's the change in T? This is going to be constant. It's 0.1, 0.1, 0.1. And this is just the difference between these two. And now you can take the velocity of HB, which is equal to change in HB over change in T. So in Excel, you can get these velocities. Cool. And then you basically have an equation for the velocity. That's what we're going to do with the chain rule. And even with this, I'm curious, because if the velocity of HB is equal to basically delta HB over delta HT, but we said this is also equal to delta HB divided by delta X times delta X divided by delta T. And because these are just one, they cancel out. But it's cool because, hell yeah, we know change in T. Change in X is going to be, because this is 0, 0.2. So change in X is always 0.2. Change in HB for one of these is going to be known. And then the change in T for this scenario is 0.1. And this would give us a value of the velocity of HB. And again, it's the same because you already got the height. You already knew the change in height. But why this is just redundant when doing it in Excel, because you're just taking something, you know, and kind of, you know, multiplying it by 1. It's not redundant if you have an equation. So now let's do our equation, because we have to take the derivative of the height of the backpack with respect to x. You know what I mean? All right, and thank God derivatives are easier than integrals. You know what I mean? Keep that in your mind, that derivatives are just like, oh, thank the Lord, it's a derivative. My life is going to be so easy, and you can just kind of do it in one go. You know what I mean? You can basically say, hey, this is on the inside, and then you take the derivative. You know, you have to take a, so I mean, it's kind of like a u substitution, but you say this is just u to the 1/2 minus, you know what I mean, a constant. Well, the derivative of a constant is 0. Isn't that right? And then why is the derivative of a constant 0? Because this is hx to, I don't even want to get into that. No, I thought I got into that last time. But no. There's a huge difference between integrating 1 over x, where this is x to the -1, and then to integrate it, you got to go -1 plus 1 divided by -1 plus 1. So right here, you divide by 0, which is an absolute, you know, hell no. Oh, no. So I think we can do it. This still is x to the 0. I just kind of freaked myself out. So what's the derivative? What's the derivative of hx to the 0 with respect to x? Well, what's a derivative? What's the derivative of x squared? So derivative of x squared with respect to x, well, just, we know that. You bring down the 2, and then this is x, 2 minus 1. Cool. You know what I mean? And I like to do 2 minus 1 because you reduce it. And that's why this is such an awesome equation for integration. You know what I mean? Always do it -1. I mean, just your power plus 1 divided by your power plus 1. And then so same thing, power minus 1. But you bring the power down, multiplied by power minus 1. Got it. So how about h to the x to the 0? The derivative of, with respect to this is bring the 0 down. Okay, now I see it. Now you're multiplying 0 by h, and you're taking x to the 0 minus 1. Now, it seems like this might be problematic, but it's not, because we'll just take it over. 0 times h, and then x to the -1 is just bring that crap downstairs. So this is just 0 times h over x. There's nothing funny here, no dividing by 0, and then you're just taking something multiplied by 0 is 0. All right, you know, you can thank me for that. No, I'm just joking. But no, I'm just satisfied that it's just like stuff like this is real important for me. And like, even if you see the number 1, well, guess what? That number 1 is 1 to the 1 power. You know what I mean? If you see a constant 2, well, that constant might be x to the 0, because x to the 0 is just 1. You know, you ever think of that? You know, the acceleration of gravity is -9.8. It's -9.8 t to the 0. You know, because t to the 0 is it's a function. Well, it's not a function of time. You know, even gravity could be t to the 9.8 x to the 0. You know, it could be a function of position. Gravity is not a function of time or position. It's a constant. So you can throw whatever you want there. Anyway. All right, let's do it. Maybe get a new sheet of paper. All right, hell yeah, welcome back. So we cleaned it up, and we basically, you know what I mean, got our major equation. That's number 1. We used the chain rule. And you know, you break it up into components. This is a constant. That's cool. And guess what? This is the derivative. But I wanted to, you know, going through all this, I was just like, oh, so I mean, if the velocity of the boy is constant, you know, I mean, 2 meters per second, you know, x is a function of time. I don't even know how you write that, but x is going to be equal to you know what I mean? Basically, your velocity of b times t. Okay, so it was kind of fascinating, because couldn't you just say that now h, your height of the height of the backpack is going to be just throw in this for you know what I mean, VB, you know what I mean, V squared T squared plus H squared, square root of that minus H. Now I have no idea, I'll have to look this up, but I mean, I thought it was going to be really complicated to make this as a function of time, because now what you could do is just take this dHB divided by dt, you know what I mean, because change in the height, divided by the change in time, and yeah, you can differentiate with respect to t. And, could I do this real fast? I mean, on the inside, you would have 2 velocity b squared would be your derivative right there, of t. So, that would pop out. And then this would be your u, and we'll do this in a second. And then you got to take this from 1/2 to the negative 1/2. So then so this whole derivative, I'll just put it down here, would be 2 vb squared of t, all divided by square root of vb squared t squared plus h squared, and then this minus h, well, that's just 0, and I can throw it in there. But there you go. I think this would be the derivative. This would be the velocity of hb. This would be the velocity of hb with respect to time. Now you got a time in there. That was wild, because it took me like 3 days to be like, to not get an answer for this. It's just like, I tried to, because now let's differentiate this. Friggin' A, let's do it. So we're gonna, so right here, here's our chain rule. So right here, it's almost nice to just put a bracket. We know we're going to differentiate with respect to t. That's where all those funny rules come in. Cool. And we're actually going to differentiate with respect to x. That's why we're using the chain rule. And then dx dt. This is a constant. So that's just a constant. We know that's velocity of the boy. Cool. Right there. So right here is where you use, maybe use brackets. And it just cleans it up. You know what I mean? So now you have the derivative of that, square root x squared plus h squared minus h. So the derivative of this whole thing with respect to x. And now we get something where, this is u to the half, and then you got something inside, which is, you know what I mean, maybe it's just du. So u is equal to x squared plus h squared. So du is just 2x, you know what I mean? And this is just 0, so cool. And then differentiating is really easy by, because you basically just differentiate the outside, which this just becomes, bring the half down, and then this just subtracts, so it's negative half. But then you still got to multiply by with the derivative of the inside, so that's pretty easy, you know what I mean? Do your derivative just like normal. And then all you got to do is multiply by the derivative of the inside. It's way easier than integration with u substitution. Then you got to pay more attention with u substitution about that factor. But this one you just pop out, stick it in. So let's do it. And this becomes 0. So we're going to take that 2x, pop it out. The half comes down. Cool. And then the u just becomes, and I can write it like this, x squared plus h squared to the negative 1/2. This becomes minus 0, that's just nothing. And cool, so now this just becomes x, so we got x squared plus h squared to the negative 1/2. And like I said, this is just the one part of it. So we just did that part, we still got to multiply by VB, and there you go. And in the problem, that was what they wanted. They're just like, and let's do this one since we wrote on it. But yeah, they're like, show that this is true. X squared plus h squared to the negative 1/2 times the velocity of boy is the velocity of the backpack at every position of x. See how it's not a function of time. And I'm not going to say that this is exactly correct, because I'll have to double check it. That's the deal with math, is just like, for the love of God, I don't know until I put the numbers in. But that's why I like Excel, because right here, we have the velocity of the backpack. So now I can put the velocity of the backpack in every point, and then associate it with all the, it's like, where's my Excel thing? You know what I mean? Excel's great. You can throw in all these change in t's. You can throw in your change in x's. You know, you're just, you know, whatever. Oh yeah, because you got the velocity of the boy. And then, yeah, and then we just found an equation. This is literally the velocity of the backpack, h of b, is there. So booyah. So then in Excel, you could find velocity of the backpack for every x. So that's what we did. For every x, we wanted to find the velocity of a backpack. Well, guess what the x is related to? It's related to that change in time. So we with Excel, you know, or graphing these graphically, you get the function of the backpack as a function of time. You can just be like, hell, I want to know, I'm just going to point to a time and then point to where the velocity of the backpack is. Cool. All right, we got it. And maybe more time on the clock. All right, now, you know what I mean? I'm going to try using as few words as possible. That ain't happening. But we want to find the acceleration of the backpack, which is, I like to do it this. This is kind of your average acceleration. But acceleration is like change in the velocity of the backpack divided by change in time. And again, you know what I mean? If you take these to real small, this is why this is the leap to here. I think it's real hard for people just to be like, oh yeah, acceleration is dv dt. You know what I mean? I just don't think, even at a pro level, you know what I mean? It'll take you 20 years to maybe like drill that. I don't know. You do you, but maybe I'm slow. All right, but yeah, we're chain rule again, because we can't differentiate with respect to t. We don't have a t. dvhb divided by dx. Heck yeah, we can differentiate with respect to x. But then we got to go dx because we got to make these the same. So it's basically just taking this and multiplying by dx on both sides. And then when you do that, you can flip-flop them like that just to make it kind of make more sense. Well, and because this is velocity of the boy again. Cool. So now let's differentiate again. And do I know how to differentiate again? Oh, and differentiating again with a product is real simple too, because it's I don't know, differentiation is way easier to integration, but you have to take the first times the differentiation of the second. So we can differentiate that, and then you got to take the second times the differentiation of the first, which is just 1. X goes to 1. Cool. So you'll just have that. So we already know that term is just going to be there. And then you have velocity of the, this is constant, so we can just bring it outside of the differentiation. Okay, so let's write it again. And then we're just going to throw this in there. With respect to x, velocity is going to come out. And there you go. So that's what I put in there. And then the velocity right there, I took it outside the integration. But this is... No. Bear in mind that this is also, yeah, I think I did it in a way that you're not going to like it. So the whole thing is the velocity. So this whole velocity component right there already has this VB in there. And I can just take this VB outside. But this VB is different than the velocity of the Boy Scout. So anyway, there you go. That's why in the end we'll have velocity of the boy squared. So do not confuse that. Just like I didn't just take this on the outside. No. I said we're differentiating this, which has a constant, which is the velocity of the boy. So we're taking that outside of this dx. But in the end, to do the whole thing, you'll still have the velocity of the boy right there. So yes, this whole thing is there. Yeah. You know, I should just put this as dvh of b over dx. That's the only term we're worried about right now. In the end, we'll add on that extra velocity. All right, and then even this, I just want to throw away and then bring it back in. All right, let's do it. So the first times the differentiation of the second. So your u is going to be 2x plus h squared. Your du is going to be 2. No. I don't even know why I hiccup there. So your u is this whole thing, x squared plus h squared. Got it? Du is equal to 2x. This goes to 0. Differentiation of a constant 0. Already done it. Okay, so now we're going to take, it's the first times the differentiation of the second. So the du pops out, so we're going to go 2x. This comes down, so we're going to go negative 1/2. And then I've made a mistake a couple times where I'm just like, I didn't keep this negative sign. This comes down as a negative 1/2, not just a half. So keep that in mind. Okay, and then perfect. And now you're just gonna your u is u to the negative half. So yeah. This goes to negative half u to the negative 3/2. So we brought the negative half down. Now we're going to go to u, so that's just going to be x squared plus h squared, and this is to the negative 3/2. All right, so we did a little bit faster. These two cancel, and then this is, oh, for the love of God, I hope I didn't mess up. No, we didn't. But this is x times negative 1. So this is negative x squared. That's real important because it'll make things makes sense. So we got negative x squared times x squared plus h to the, you know what I mean? You got to take it to the downstairs. You got to cube it and then take the square root of it. That's what that means. Okay, so now that's the first. That was the first times the derivative of the second. Now we got to take the second. Oh, thank God, that's easy. And it's additive. So it's x squared plus h squared to the negative 1/2 times the derivative of the second, which is just 1. But now you got to clean this up, because that's why this problem's cool, but it's kind of a pain in the butt. You know what I mean? Because this negative, we're going to take them all downstairs and put them into fractions. We're going to go negative x squared. So then this kind of makes sense. We're going to keep the parentheses though. And this is 3/2. This is added to 1 to the x squared plus h squared to the 1/2. Now, how do we get our denominators the same? Let's say this was 3 and this was 1. So we got 1 over 3 plus 1 over 1. Okay, we'll just multiply this side by 3, and now you would get 1 over 3 plus 3 over 3, and you could go 4 divided by 3, which 1/3 plus 1 is 4/3. Cool. So we're doing the same thing here. We're just multiplying by x squared plus h squared to the 1 power. So this is a real good place to actually put in your 1, because 1 plus 1/2 is 3/2. And even this, instead of putting in 1 here, do 2 over 2, knowing that 2 over 2 is 1. So 1/2 plus 2/2 is equal to 3/2. Cool. But if you did something downstairs, you got to do the same thing upstairs to multiply by 1. And then so we'll do the same thing. I'm just going to do the 1. Got it. So now we can just add. Now the denominator is going to be the same. We don't add the denominator. We just keep it, but we can add the numerators. And this is cool because the numerators, I'm just going to do it up here. It's negative x squared, because this is cool. And this is 1 times this. So it's negative x squared plus x squared plus h squared. Well, guess what? Those two cancel, and you're just left with h squared. Hell yeah. So and you'll see in a second, this doesn't even have an x term upstairs. So now we just have h squared. So you get this, h squared, and then you could do all the downstairs stuff, but we'll bring the downstairs back upstairs. H squared plus x squared. Let's throw some more time on the clock so I don't lose my mind. Hell yeah. Yeah, I don't want to lose a drop of this footage. Okay, so, yep. And then with negative 3/2. Hell yeah. So we basically did it. And like I said, though, that velocity of the void that we threw away right there, we got to add it in. And then, but this was, and so we'll just do that. We'll just add it in. But this whole thing right here, again, was just the differentiation of velocity with x. And I got to take a little break. Alright, hell yeah. I had to take a little break, get that light going. But again, this right here is not the acceleration. This right here was, all we did was take the derivative of the velocity of the backpack and with respect to its position. But we said the acceleration of the backpack was the derivative of the velocity of the backpack. We'll have to go up here. No, we just did the chain rule. It's the derivative of the velocity of the backpack times the change in x, change in t. Change in position, change in x, change in t. That's the velocity of the boy. So we took the derivative. That's this part. We still got to take the multiply by the velocity of the boy. So we would just do that with v squared. And hell yeah, that's it. I'm about out of breath. You know what I mean? But yeah, so that's that component right there. So you got h squared. Hell yeah. I don't know how to put them on the same page at the same time. But there you go. You got h squared plus x squared plus h squared. And this again, you know what I mean? I think it's good. The negative brings it downstairs. And then the x squared plus h squared. The 3 powers it to the 3. The 1/2 part of this, because even this, so negative 3 halves is just equal to negative 3 times 1/2. Okay, so you're powering it to the 3, you're cubing it, and then you're taking the square root of it. And then the negative just means all that crap's going to be on the basement. Okay, so you can rearrange this however you want. That's it, that's it. And now, you know, you could solve the problems, you know what I mean? It says, let height equals 3 meters and the speed, assume that the food, you know, what the hell do they want? They don't even want anything, you know what I mean? But basically, you could figure out the velocity of the backpack at every point. You could figure the velocity of the backpack right before it hits the top. Well, let's do that at least, you know what I mean? If we, yeah, let's take a little moment of pause. All right, hell yeah. Now, yeah, well, let's throw in some values, you know what I mean? They already gave you, this problem's so hard, they even just gave you the velocity and the acceleration as a function of x. But we kind of want to know what the velocity at the top is going to be. You know what I mean? So, we got our velocity, it's 2 meters per second of this guy going this way. And then we got the height is 6. Okay, so, I mean, the velocity right at the top, you know what I mean? And when, shoot. Yep. Oh, this is we need to find the x value when h is equal to 6. So we actually even need to go back to our height of the backpack equation. What the hell was that? That's cool. That's cool. Height of the backpack equation. Did we even get it? Yeah, x squared plus h squared minus h. So this is x squared minus x squared plus h squared. X squared plus h squared minus h. Yeah, so we need to, so when this is 6, we actually need to solve for x. That's interesting. So we're going to have 6 plus 6. That's where you get the total height. That's 12 meters. So see how this is 6 right here? This is 6, but we're going to add it over here. So you get 6 meters plus, so you got 12 is equal to, and then we're going to square it. And that's going to equal x squared plus h squared. This is just 6 squared. This is 36 plus 36. So you're going to have 144 over here minus 36. You can bring that. That's going to equal x squared. And then you're going to have, I'm 144 minus 36, 108. And then you're going to, x is equal to the square root of 108. Okay, so the square root of that is going to be 10.4. And that'll be a little bit higher, but whatever. Okay, so when this boy's 10.4 meters out here, this backpack will rise up 6 meters. Cool. Okay, so now we can do it. So now we got 10.4 times 2 meters per second for the velocity of the boy. And then we got 10.4 squared. Hey, that's about 100. Plus 36, you know what I mean? Because that's 6 squared. We'll just do it like that, I guess. But we got to square root that. And this give us that. This is not minus, this is multiplied. So we got 10.4. Store that as x squared plus 6 squared. Square root of that. Store it as a. 10.4 times 2 divided by a. Okay, so the velocity is 1.7 meters per second. And like we said, when this guy gets way out here, the velocity is going to approach 2 meters per second, you know what I mean, as this goes to infinity. Got it. So that works out. Now the acceleration, when something's at stopped and then it starts to move, that's where you might have the most acceleration. Ah, damn it. All right, hell yeah. All right, so I'm so glad I'm doing this analysis. So where were we? So we found that, I don't even know. Yeah, the velocity. Velocity of the backpack at the top is 1.7. Velocity of the backpack at the bottom is 0. And it's hardly anything as we go up. But the crazy thing is, the acceleration at the bottom is bigger than the acceleration at the top. Because like we said, the velocity at the top is basically becoming constant. And the definition of acceleration is change in velocity. That's the top component. And this is becoming, there's zero change. It's a constant. It's trying to hit constant velocity. So the acceleration at the top is lower than the bottom. So let's look at the acceleration at the bottom. That's an easy because x is 0. And then this is 6, this is 6, this is 2. Cool. So we're going to go 6 squared. And then we're going to cube it. And then take the square root of that. And this is going to be, store that as b. This is going to be 6 squared times 2 squared. And that's 144 divided by b. Perfect. So the acceleration at the bottom, t is equal to 0 or whatever, is 0.66. Oh, and this should be acceleration of the pack when h of b, you know what I mean, is equal to 0 if you want to get technical. Anyway, blah, blah, blah. So now we want to find the acceleration of the pack at the top. We'll just do top. And that's going to be when this is 10.4. Because we said when the boy is out 10.4 meters, pack's at the top. All right, so hell yeah, let's do that. So we're going to go, I guess we're the same thing, h squared times 2 squared. That's 144, stored as a. And then the bottom, we're going to have 10.4 squared. Plus 6 squared. And now you can do either one first. You can cube it, then take the square. Let's take the square root of it because it's close to 12, and then we'll cube that sucker. And then we'll store that as b. Alpha a divided by alpha b. Damn it, I don't think I did it right. So this is 10.4 squared plus 6 squared. And then we're going to cube it and then square root it. And then, damn it. Well, why is this smaller? Oh, no, this is at the top. No, this is exactly. I thought I already tried to do this before. So this is stored as b. And then 6 squared times 2 squared is the velocity of the boy. So it's 144 divided by b. Yeah, it's small. It's 0.08 meters per second per second. And what do we know about gravity? And this is only, you know, the acceleration on this is real slow anyway. You know what I mean? If you dropped if you reverse gravity and you dropped a rock right here, it would hit the top of the tree like 0, 1. And we're talking this hits the tree. You know, that's the other thing you can figure out. Like when the hell, at what time is it going to hit? I don't know. But yeah. So your acceleration at the top is low, but your acceleration at the bottom is interesting. So before this system even moves, the weight of the pack is just mg. It's got its weight. But the fact that you're having to accelerate it up at any substantial amount, this increases the force that you're going to have to pull on this. Let's say you're just pulling straight up, you know, heaving this pack up a cliff. So if you're accelerating, if you're changing the velocity of the pack, then you're having to pull its gravity, or its weight in gravity, mg, plus its acceleration. You know what I mean? So those are additive. All right, got some more light going. Okay, so yeah. So, and we need a free body diagram. So here's the pack, and then at rest, when there's no motion, you're just going to get the weight mg. But when you do have an acceleration in this direction, the force and the tension in this rope is going to increase. But when that acceleration gets to the top, this acceleration almost goes to 0. So then the force, the tension in the rope is going to go back just to the weight of the pack. Now, if you pulled on this rope fast enough, like if you had a machine pulling this rope, you know what I mean, and you got a number that was like 9.8 meters per second, well, now it's substantial, because now you have the mg of the weight of the pack, plus you're changing its acceleration by 9.8, you know, another mg. So this pack's gonna, the tension in the rope is gonna be 2 mg. You know what I mean? So that's where always in physics, especially with mechanisms, acceleration is king, because F equals ma. So if you are accelerating a mass, it's going to take a force to do that. And if it's only secured by a rope that only has so much force it can take before it, you know what I mean, breaks, then you can only accelerate a mass. You can only change the velocity of the mass over a certain period of time. You know, you can't like instantaneously move something, else you're gonna break a rope. That's why even if you just like yeah. So that's fascinating. All right, hell yeah. Well, thanks for joining me. This problem, you know, because it has a trigonometry at the beginning, those are always the most challenging. For me, they are. You know what I mean? Trying to figure out triangles and a little change in something. So that's set up, but I love this because it also has, you can't just differentiate with time, you have to use the chain rule, so you got to differentiate with the variable you have in the equation, which is x, and then don't forget to add that change in x, change in t velocity. So anyway, man, I need to charge my light before we can do another video. Thanks for joining me, and guess what? That's a video.